All right, guys, in chapter 5, we're going to talk about probability and we're going to talk about the normal curve. So the first thing we're going to talk about is how do we calculate a probability and what are the rules of probability. So up until this point, we've been drawing conclusions about data we've actually observed. Okay, so we could sit down, we can observe 10 people taking a test, we can get their 10 test scores. That's actual data. The cornerstone of decision making, though, is probability. What's the likelihood of any one particular thing occurring of any given outcome or event? Okay, so that's the number of times an event can occur relative to the total number of times any event can occur. So let's think about flipping a coin, right? A coin has a heads and a tails, right? So when I flip it, right, heads, that's one event and it can occur out of two possible events. So probability varies from 0 to 1 and it's expressed as a decimal. The closer you are to 0, it's very unlikely. The closer you are to 1, it's very probable or likely. 1 means it's absolutely certain. So P equals 0 means the outcome is impossible. P equals 0.5, it's just as likely to happen as not happen. And P equals 1, it's absolutely going to happen. So, probability is the number of times the event can occur over the total number of times any event can occur. Now, there's some rules here. The converse rule is the probability that something will not happen. That's 1 minus P. Okay, so if the probability of something happening is 0.4, the probability of it not happening is 0.6. 1 minus 0.4. Okay. The probability of obtaining one of several different and distinct outcomes is the probability of the first event plus the probability of the second event. The probability of obtaining two or more outcomes in a combination is the probability of the first event times the probability of the second event. So let's flip a coin 2 times. The probability of getting heads on the first flip is 1 out of 2, or 0.5. The probability of getting heads on the second flip is 1 out of 2, or 0.5. The probability of getting heads on both flips is going to follow the multiplication rule. That's 0.5 times 0.5, which is equal to 0.25. What's the probability that one flip out of 2 will land on heads? Well, that's going to be addition. Okay, not that both flips will land on heads, but that if I flip it twice, what are the odds that one of them will be heads? So that's the odds of the first event and the second event, 0.5. So what's a probability distribution? We talked about frequency distributions, okay? And this is very similar to that, except it's based on probability and all the probabilities sum to 1. Okay, so the mean is mu, it's not x bar, and standard deviation is this sigma here, this O, as opposed to s squared, or s rather. Okay, so probability distribution is based on what should happen, right? If I flip a coin twice, one time it should be heads, right? It should be heads or tails, okay? But what actually happens? So the frequency distribution is what did happen. So probability is like a frequency distribution, but imagine we're going to flip that coin an infinite number of times. So probability, as I mentioned, has a mean, and that's mu. Okay, it's that m. Standard deviation is sigma, and variance is sigma squared. So here we've got them compared. Okay, for a frequency distribution, the mean is x bar. In a probability distribution, it's mu. In a frequency distribution, the variance is s squared. In a probability distribution, it's sigma squared. Standard deviation in a frequency distribution is s, and in a probability distribution is sigma. So now let's talk about the normal curve. A normal curve is a theoretical or ideal model, and it comes from a mathematical equation. Okay, we can use it to describe a distribution of scores. We can use it to understand standard deviation and to make statements of probability. So what does a normal curve look like? It's smooth, symmetrical, and unimodal. Okay, unimodal means it has one mode. In a normal curve, the mean, median, and mode are all the same, and it continues on infinitely in both directions. It's also not a frequency distribution, it's a probability distribution. So its mean is mu, and its standard deviation is sigma. All of the area under the normal curve represents 100% of the probability distribution. Remember, it's a theoretical idea, and not all variables are going to conform to this. Okay, most data is not going to be normally distributed. Most distributions are skewed, multimodal, or symmetrical, but not bell-shaped. Okay, a normal curve is a bell curve. We don't want to assume that our data is normally distributed if it's not, because it can screw up our conclusions. So here's our normal curve. Okay, notice it's smooth. It's symmetrical, which means we can fold it in half and each half will match, okay? And it has one mode. 100% of the area is underneath the curve. And it's showing you one standard deviation, one sigma. The distance between mu, the mean, and one standard deviation, one sigma, is 34.13%. The second standard deviation is going to be, the area for 1 and 2 standard deviations is 47.72, and for 3 standard deviations is 49.87. And what you see on the right side of the curve is also on the left side of the curve. Okay, so in the middle, a little over 2/3 of all scores are going to be within 1 standard deviation of the average on either side. 95% will be within 2, 99% will be within 3. Okay, so another measurement we're going to use here is what's called a Z-score. How do we take that sigma distance, just like we talked about standard deviation before, okay? How can we determine the distance from the sigma distance of any given raw score? How do we translate that, okay? We're going to use what's called a Z-score. So we're going to take any given raw score in sigma units, divided by the distance of the raw score from the mean of the standard deviation. What a Z-score does is it tells us the strength and degree that any given raw score deviates from the mean of a distribution. This is going to mean a little bit more to you as we get into these. Okay, so the distance is the Z-score. It's going to tell us direction and distance. Okay, so Z is equal to X, any given score, minus mu, which is the mean, divided by sigma. Pretty easy calculation. Okay. When the normal curve is used in conjunction with a Z-score, and we can use table A to look at Z-scores, we can determine the probability of obtaining any raw score in a distribution. Okay, we can also reverse this process as well. So let's look at a problem here. Let us return to an earlier example looking at response times for emergency calls into a 911 system. Okay, the distribution of response times was normal, right? And the average was 5.6 minutes with a standard deviation of 1.8 minutes. So that would mean then, right, that 2/3 of all scores are within 5.6 plus 1.8 and 5.6 minus 1.8. Okay, so we learned earlier that an 8-minute response time was 1.33 sigmas above the mean of 5.6 minutes. Okay, so Z was equal to plus 1.33. Now let's use that to determine the probability of obtaining a response time. So what are the odds that we're going to get a response time between 5.6 minutes and 8 minutes? Okay, so a call goes into 911 and the response time is between 5.6 minutes and 8 minutes. Okay, we can do this pretty easily. We're going to take that raw score, 8 minutes, and turn it into a Z-score. So that's going to be 8 minus mu, 8 minus 5.6, divided by 1.8. So we know the raw score is 1.33 sigmas above the mean. Then we're going to take table A, which is in the back of your book and on Blackboard, and we're going to find the percentage of total area under the curve falling between the Z-score and the mean. Okay? When we do that, we would find that 40.82% of response times are between 5.6 minutes and 8 minutes. We're going to change that to a P. Okay, probability 0.4082 is the odds, that the probability we would obtain a response time between 5.6 minutes and 8 minutes. So on the basis of a normal shape of response distribution with a mean of 5.6 minutes and a standard deviation of 1.8 minutes, 25% of response times are 6.8 minutes or longer. Okay, we can also find a score using the probability. So let's continue with this response time distribution. Okay, it's got a mean of 5.6 and a standard deviation of 1.8. Let us find the cutoff for what are the quickest 20% of calls. Okay, so in table A, we want to look for the Z-score that cuts off the area closest to 20% below it. Okay, so we're going to look through column C on table A for the area closest to 20%, and we see that 0.84 cuts it off. Cuts it off at 20.05, close enough. Okay, so because it's below the mean, we're going to use the negative, so that Z-score is negative 0.84. We're then going to convert that back into a raw score. So this is just like plugging it into the formula and solving for the raw score, solving for X. So we're going to put in our mu, which is 5.4, minus Z times our sigma, and we're going to find 3.9. So about 20% of calls to 911 are handled within 3.9 minutes. 80% of those calls take more than 3.9 minutes. Hopefully that makes sense.